Without further ado, let me tell you all welcome, and let me introduce myself. My name is George Haddad. I'm actually a neurosurgeon, so I was operating this morning, hoping I'll finish on time to be here today. So in a previous life, I did my BS in physics, and I want to start by thanking Dr. Khalil Bitar for suggesting my name to give the lecture, and thank Dr. Nader Bizni and Dr. Peter Shbai'a for allowing me to be with you here today. So let us start about a brief history of time. I'll try to make it as interesting as possible. There's going to be only two equations, but just for you to look at, not to understand, don't worry about it. And I hope it will be fun for you as much as it was fun for me. It all started with Aristotle. Aristotle, was born in the 4th century before BC, and he had three main ideas that all made sense. The first idea that made sense is that the Earth is in the middle of the universe and everything goes around it. This is what we call geocentrism, okay? Unlike what they told you in school, nobody believed at the time that Earth was flat. It's only when the church came and they decided that the Earth was flat. The Greek knew that the Earth was round, it was a sphere. But they placed it in the middle of the universe. And this is what we call geocentrism. And Aristotle, being a reasonable man, said, if I don't push something, it does not start. It does not go into movement on its own. And to keep it in movement, I have to keep on pushing it. مثل واحد بدفش السيارة. بلش ادفش إذا بوقف السيارة. This is because he did not know about anything called friction. And it made sense. The third point is that he decided, or the Greeks decided, that everything in this universe, you, me, the world, the universe, was made out of four elements. There was earth, water, fire, and air. Okay, so earth, water, fire, and air. And for those of you who like pop music, in the 1970s, there was a pop band called Earth, Wind, and Fire. And the name of the pop band was actually inspired by Aristotle. And Aristotle said, that's great. Anything that is made out of earth or of water will tend to fall down because it wants to go to the place where it came from, to the place of predilection, to the center of the earth. Anything that is made out of fire or out of air goes up towards the moon because this is where it belongs. So for Aristotle, things were easy. The earth was in the middle of the universe. To put something in motion, you had to push it. If you stop pushing, it will stop moving. And depending if you were made out of earth and water, you would fall down. Or if you were made out of air and fire, you would rise up. 2,000 years later, Newton comes in. And Newton is going to change all this. The first thing he's going to do is that he's going to talk about the law of gravitation, how things attract each other. And the law of gravitation is very easy. He's telling us, I'm attracting you and you're attracting me. Okay? You get attracted to each other in a way that is proportional to the masses and inversely proportional to the square of the distance. Which means the closer we are together, the more attraction there is. The further we are together from each other, the less attraction there is. Okay? This is gravitation. And then he had the three laws of motion, and I'm not going to talk about the mathematical way of saying it. Let's just go to the down-to-earth way. The first law says that an object at rest will remain at rest unless acted on by an unbalanced force, by a force. But this is the most important thing, that an object in motion continues in motion. So if I give somebody a pat and put him in motion, he'll keep on going forever unless I give him another pat to stop him. And that was very important. And he said that, okay, you get attracted to the earth. So it's not, we're not talking anymore now about if you're made out of water, you're made out of air or whatever. And every two bodies attract each other. So just to cap on, Aristotle, geocentrism, Newton, heliocentrism. By that time, we knew that the sun was in the center of the universe. Okay? Aristotle, motion needs a force. For Newton, a change in motion needs a force. If you don't have to change the motion, if you're going in a straight line, you don't need to put a force, okay? And for Aristotle, things go to their place of predilection, whereas for Newton, there is the law of attraction. So now we're going to get into relativity, okay? And I want you to bear with me for a few minutes. I always like these schemes because men are walking on the train, not in the train. It's easier to see them on the train. So here we have a train that is actually going at 40 kilometers an hour. Okay? In 1 hour, okay, the train would have gone 40 kilometers. But I also have a man walking on the roof of the train at 10 kilometers an hour. So in 1 hour, the gentleman would have moved actually 50 kilometers because the train is moving 40 and he's moving 10 on top of the train. So within 1 hour, he's moving, okay, 50 kilometers. This is what we call relativity of speed. If I speak to the gentleman here and I tell him, how fast are you going? He would say, I'm walking at 10 kilometers an hour. If I ask the driver of the train, how fast are you going? He will tell me, I'm going at 40 kilometers an hour. Me observing both of them will say that the gentleman is actually moving at 50 kilometers an hour, okay? And like you can add speed, you can actually subtract speed. Now we have a robber, this is a Western movie, who's running on top of the train and he's being followed by policemen. There's a policeman running behind him and the policeman is standing on the sideway also, and both are shooting at him. And these are very quick bullets. The bullets are 100 miles per hour. If the train is going at 50 miles per hour, this bullet, the bullet of A, will hit the robber at 100 miles per hour, okay? The bullet of Mr. B here, who's standing on the roadside, will hit him at 100 minus 50, at 50 miles an hour. The way for you to understand it is that if you're sitting still and somebody gives you a sahsuh, you go much further than if you're running and somebody gives you a sahsuh, because you're running, you don't feel it as much as if you're standing still. So, like you can add speed, you can subtract speed. Okay, if you forget everything about the lecture, please remember this slide because we're going to get back to it, okay? Speed is relative. Now let's put speed to the side and we're going to talk about light and then I'll speak about both of them together. So this is Hong Kong at night and light was always a problem because from the beginning we had two theories of light. The first theory was that light is made out of corpuscles, that light was discrete. What is something made out of corpuscle? What is something discrete? It is like if you're playing the piano. You cannot play between two keys. You have to play either on do or on re. You cannot play in the middle, okay? So a piano has discrete touches, and this is what we call the corpuscular theory of light. That light is made out of small bundles of small, bodies, and this is what Newton had in mind. Now, if you're playing the violin, okay, you can really put your finger anywhere you want on the string. And this is a wave. So if light is a wave, you can actually, subdivide it in any which way you want. And the most important person who thought about this was Huygens. And they kept on fighting back and forth that light was made out of matter or that light was a wave. Well, if light was made out of matter, okay, this is what we're looking at here. It's particles. The shadow has to be a straight shadow, okay? Matter does not bend, okay? Waves bend, matter does not bend. And Newton told everybody, Ya Jama'a, I've never seen a shadow that was not straight. And then Huygens said, no. If you make here a very tiny pinhole, okay, the light will open up. And the shadow will going to be also rounded. And they kept on fighting, and we'll see how we resolved it. Now, what is a wave? A wave, as I told you, is like a violin. Okay, you can subdivide it any which way you want. But more interesting, a wave can either add up, and you can see here, these two added up to become much higher, and these two canceled to become much lower, okay? Or they can also cancel, okay? This and this will cancel, and this will cancel, okay? When do you hear this? When you are going in your car and you have the FM and you go into a tunnel, okay? When you go into the tunnel, when the waves add up in the tunnel, the sound will be very, very clear, and when they cancel, you will lose. And then a little bit further, you're still in the tunnel, you hear again the wave, and then you lose it again. And actually, doing some calculation, you can know how what the FM is just by keeping track of when you're losing and when you're getting your radio. So this is a water wave, okay? بننزل كلنا بنتسبح بالمي بنطبش بالمي وإلى آخره. Okay? This is a small hole. A waterfront comes here and then it will radiate and becomes and will open up. This is what a wave does. If I have two small holes here, I will have two wave fronts that are going to combine. Okay, they are going to cancel where the trough is, and they're going to add where the crest is. Okay? We all think that speed, or people thought that speed was actually instantaneous because it was so quick. And yet, all the way back in 1676, people knew that there was a finite speed of light. And believe it or not, in 1809, they calculated it to be 300,000 kilometers per second, which is more or less what we're dealing with nowadays. So 200 years ago, people knew that light went at this speed, and this is a speed that actually allows light to circle the Earth 7 times in 1 second. Mr. James Maxwell, he actually came out with the idea that electromagnetic waves are going actually over a whole spectrum, and that light is only part of this electromagnetic wave, okay? So if you look at this, here you have, okay, the TV, okay? Here you have the AM radio, here you have the X-rays, the gamma rays. All these are the same rays, okay? مثل واحد بيقول لك عند السيارات كل واحد نوع شكل بس كلهم سيارات. So Maxwell, by combining these, came out with the idea, and it was only on paper at the time, that the speed of these electromagnetic waves did not depend on the observer. You remember when we said that speed depended on the observer in the train? Maxwell comes in and said, Ya Shabab, it does not depend on the observer. These electromagnetic waves will go always at the same speed, no matter where you are, no matter how you look at them, no matter what. And light being part of the electromagnetic wave, he said then light has a finite speed. And this speed will not change, okay, depending on the observer. I want just to clarify a moment before a notion before going further. This is a red light, orange light, green light, and violet light. They all go at the same speed. They will all go from here to here in the same time, okay? Speed of light does not change in vacuum. So they will all go at the same speed. The two things that are going to be different is that how many times they go up and down, which is the frequency, or the wavelengths. It's exactly the same concept. So when you have a long wavelength, you will see red. Okay, if you have a very short wavelength, you will see violet. Okay, below the violet, okay, so above the violet, this is what we call ultraviolet, and we cannot see it. Below the red, this is what we call infrared, and we cannot see it, okay? So the speed is the same, the frequency and the wavelength differ, and the amplitude, what is the amplitude, is how high it is, okay? So I can say, oh, it is the same, okay? It is the same wave, but an amplitude is high and amplitude is low, okay? So people decided, okay, if light is a wave, it has to have a medium. يعني water waves, you need water to have water waves, okay? You are able to hear me because there is air. If there was no air, you could not hear me. You cannot hear somebody in vacuum. So people said, okay, if light is a wave, we need to have a medium, and this is what they called ether, okay, al-athir. And they started looking for this medium, and these two gentlemen in 1887, Michelson and Morley, decided to actually go ahead and do an experiment to find this medium. And their idea was very easy. They said, I'm surfing. If I surf with the wave, I go very quick. If I surf perpendicular to the wave, I go much slower. So what they did is that they sent a light beam this way, a light beam at right angle, and they saw how long it took for them to come back. And they decided if there's a difference, then there is a medium. If there is no difference between them, then there is nothing. And this is what was called the most important failed experiment in the world, because they found out that there was no ether. And them working in a university, and universities being always strapped for cash, they actually put the apparatus, in the basement of the dormitory, because they will not give them a laboratory. And to make sure that the tram that was passed by nearby did not move their apparatus, they actually made it float in a trough of mercury. يعني احنا هلا قمنا الميركوري thermometer because it is toxic. هونيك عبوا بالبيسمنت of the dormitory بركة عبوها mercury وحطوا الاباراتس عليها. It failed, and this is how things started. So until now, things made sense. From here on, I'm going to start talking about counterintuitive. Counterintuitive, if you open in the dictionary, is different from what you would expect, not agreeing with what seems right or natural. So for now, try to put your common sense على جنب, and let us go into relativity with, the three conflicts. The first conflict, and we spoke about, was the speed of light. As I told you, Maxwell, writing on the paper, found out that the speed of light was not relative. And people tried as much as they could. And then there was this young gentleman, Albert Einstein, who said, if Maxwell found this, I'm going to go from that point of view and say that the speed of light does not change. Einstein graduated from the Polytechnic in Zurich and wanted to become a university teacher, but he had made himself so many enemies at the university that they blocked all his applications. So he had to go and work, in the patent office in Switzerland. And from the patent office, bala peer review, bala ta'hanak, and all of these, in 1905, he publishes, شو صار هون؟ sorry. He publishes, 4 papers that will change, the face of science. 4 papers in 1 year. 4 papers in 1905, and I am sure that at that time, this is what he told his professor, خرجك. So let's talk about these 4 papers. I'm not going to take them in order. I want first to go to this paper, which is E equals mc squared, where he says that energy and mass are equivalent. And this is what will give rise later on to nuclear power, to the nuclear bomb, and all that. Then remember, in 1905, the atom was not discovered. Nobody knew about the neutron, nobody knew about the proton. So the second paper, which is this one here, this one here, explains that atoms do exist. And there is one more paper here that is special relativity, and we'll talk about it, and the photoelectric effect, and we'll talk about it. So in 1 year, he writes 4 seminal papers that will change, the face of science. And these are the 4 papers. Einstein had several theories. For today, we're going to talk mostly about special relativity and general relativity. E equals mc squared. Everybody knows this. This is the most important, the most known equation everywhere. You have it on T-shirts. E equals mc squared. But how can light then have energy? Light does not have mass. This is not the complete equation. For anybody who wants to brag, this is the equation, and P here, stands actually for the momentum of the particle. So this paper that changed the face of the world, that gave us the atomic power, the atomic, okay, was 3 pages long. 3 صفحات. Okay? And in this paper, he actually, okay, combined energy and matter into something called energy mass equivalence. Okay? Now, let's go to relativity. I promise you we're going to talk about relativity today, okay? What does relativity mean? Relativity means that the same laws of physics apply to anybody. To me here, to somebody in the plane, to somebody in the car. It's not إنه إذا أنا هيدي تركتها بدوقة، إذا حدا تركها ما بدوقة كذا. The laws apply to everybody. And he took this for granted. He said, okay, the velocity of light, okay, does not change with the observer. So let's try to write a theory where the velocity of light does not change. هلا حنناموا هلا. You remember this, don't we? We said that for Newton, this is what it was. The gentleman seems to be going at 50 kilometers an hour for an observer. And for Newton, as we said, okay, bullet B will actually hit the rubber at 50 miles an hour, not at 100, because 100 minus 50. Well, if they were actually shooting lasers at him, light, okay? If they were shooting him with light, the light will hit him at exactly the same speed. Okay? This is what relativity is. Okay? Relativity tells you that at the speed of light, okay, you don't have any more relativity, okay, of speed. Speed is constant, okay? And Einstein, believe it or not, hated the word relativity. He did not want it. He wanted to call it the theory of invariance because the speed of light will not vary. Okay, but people decided they're going to call it relativity, and that's what we are stuck with. So special relativity tells you that unlike the Newtonian system, where you can add and subtract speeds, when you speak with light, you cannot add or subtract a speed. So, what is speed and what is velocity? They're not the same thing, okay? Speed is distance divided by time, okay? Velocity is a vector, okay? This means that these two vectors, okay, have the same speed, but they do not have the same velocity, okay? These two are exactly the same velocity too because they're parallel. And this is important, okay? Any vector, for whoever here has done math or engineering, any vector can be actually decomposed in the sum of 3 vectors, okay, in a 3-dimensional space. In a 4-dimensional space, you can have 4 vectors and so on and so on. So speed can be decomposed into several components, and we'll see why this is important later. Halla, we spoke about speed, and we said that speed is what? Is distance divided by, divided by time. Distance, we all know what it is. بمسك مزورة وموزر. But how do you define time? When you come to define time, this is a big problem because this is when you have a problem with the chicken and the hen. What came first? And one of the definitions of time is that which is measured by a clock. And what is a clock? Is something that measures time. No, not really. A clock is something that has a perfectly regular cycle of motion. So one of the clocks that you can devise is this one. Okay, I have a photon that goes down, hits a mirror, goes back up. Every time it goes through a cycle, I call this a second, okay? So if it goes 4 times, I have 4 seconds. It goes 10 times, I have 10 seconds, okay? If this clock is on a train, this is the motion of the photon. It will not go up and down, it will go as a zigzag, okay? Listen to this. This is very important because this is how we're going to understand relativity. If the clock is on a train, the motion of the light is not up and down. It will go on a zigzag. And to prove you this, we're going to look at this movie. And You saw it went back, up and down, up and down. Now, let's look at the same movie, the same exact movie, but now let us put actually a graph on the wall to see the motion of this ball that we thought was going vertically, okay? And when I put a motion, we'll start from the beginning. Okay, so now I'm going to let my light go out, and it goes vertically down and up, okay? And this is my clock. But the clock being on a train, look, this is the graph it's going to take. Look at the ball, and what you thought was actually a vertical movement is actually a zigzag movement. You see it? Okay. So on a train, the clock will not go vertically. Okay, it will go as a zigzag. And this means that the path of 1 second is longer. Okay? This is 1 second here, and this is 1 second on the train. So the second on the train, okay, will be longer than the second in somebody who's not moving, And this is why we say that time goes slower if you are moving, okay? This is the special relativity. Time goes slower if you are moving. It is from that, okay? Now, for reasons I'm not going to get into, not only time goes slower, but also, okay, the dimensions in the direction of movement become shorter, okay? So I'm sitting here, my friend is on the train, I can tell him, look here, the length here is getting shorter, and your time is slower on the train, okay? Time going slower is called time dilation, and the shortening is called Lorentz contraction. Now, like everything in life, when things are relative, my friend on the train can tell me, yo, no, it is your, okay, because you're moving, and I'm on the train, I'm not moving. The whole universe is moving by me. So your clock is going slower, and your distance is getting shorter. Okay, and this is where the term relativity came from, is that not only is time relative, but also distances are relative. Okay, time and distances being relative, you lose the concept of simultaneity. So if I see something happening at the same time on a train, okay, a lady talking to a gentleman, somebody at the standing on the roadside might not see it happening at the same time. So two events that happen at the same time for one observer do not happen at the same time for another observer, and vice versa. Now let's talk about space-time. I told you I'm going to tell you about new things, but there's no easy way of doing it. What is space-time? Space, we said, is, okay, 3 dimensions. Okay? So if I have a ruler, I just need one number, 3, and I know where I am. I can tell you 7 and you're here. So in a one-dimensional space, all what you need is one number. In a two-dimensional space, you need 2 numbers. I am at 4 and 6, it will put me here, okay? In a three-dimensional space, you need 3 numbers. يعني إذا أنا قلت لك أنا على بليس, this is 1 dimension. التقاطع مع جان دارك, another dimension. بالبنية على الطابق السابع, 3rd dimension, okay? So 3 dimensions, we need 3 inputs. 4 dimensions, إذا قلت لك لاقيني هوني بتقول لي أي ساعة؟ بقول لك ساعة 7 عشية, this is my 4th dimension. When we combine this is what gives us space-time. Space-time is a 4-dimensional, okay, contraption where space and time are equivalent, okay? It's not space and time. Is that you need just 4 things to make clear about where you are. So special relativity is restricted to the flat space-time known as Minkowski space. Flat, I'll come back to flat, okay? Minkowski, I put it here not just to put more names, but because Minkowski actually taught Einstein, okay, mathematics. And he called him a lazy dog. And when Einstein came out with his special relativity, Minkowski could not believe that Einstein actually created all this. And he really made his best, not to help him. And then he had to say that he was a genius. And this is why we say that special relativity is restricted to the flat space-time known as Minkowski space. So all objects in the universe are always traveling through space-time at one fixed speed. What Einstein says in the theory of relativity, إنه أنا وياك والطيارة والسيارة are all going at the same speed, but not in 3 dimension, in space-time. Okay? And this speed is the speed of light. To explain to you what it is, this is space-time vector, and I told you it needs 4 inputs, مش Let us divide it into 2 inputs. One that is space component and one that is time component. يعني أنا قلت لك رح لاقيك بهيدي البناية الساعة 7. البناية نفسها هي space component. الساعة 7 هي time component. Okay? I'm not moving. But time is passing by. So for somebody who is not moving in space, all the movement he does in space-time is in time. هيدي مهمة تسمعوها. For somebody who is not moving in space, all the movement he does, is done in time. For somebody who is moving very quickly, For somebody who's moving very quickly, most of the movement he's doing is in space. So light does not feel time. Photons do not decay, not because they're eternal, but because they don't feel time. They go at the speed of light, so they only move in space. They do not move in time. We decay because we move in time and we don't move too much in space. So what Einstein said in relativity is that we all go at the speed of light. We all go at the speed of light. But depending how your vector is tilted, how it is divided, we normally experience space and time this way. Light will experience it this way. So in 1905, also in this second paper, Einstein combined space and time in space-time. I said there are 3 conflicts. Let's go to the second conflict. The second conflict was attraction. Attraction, as we said, was discovered by Newton. But even Newton knew that there was a problem. And Newton wrote, he said, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall for it. So Newton writes about gravity, and he says gravity is instantaneous, but I don't know how it works. I have no clue how it works. And at the end, he says, but whether this agent be material or immaterial, I have left open to the consideration of my readers. So for Newton, if the sun suddenly went away, the earth instantaneously will be flung off, on the split of a second, instantaneously. But he did not understand that. And that was the second problem that Einstein had to tackle, because Einstein did not like this idea. So he came out with the idea of curved space-time. Now we know what space-time is. Space-time is 3 of space and 1 of time. What is the difference between flat and curved? I told you I was going to tell you the difference. Flat is these 2 spaces, are spaces 2-dimensional. Why? Because here I only need, 2 points to determine. 6 and 1 is here. 8 and minus 6 is here. This is a 2-dimensional flat space. This also is a 2-dimensional flat space. On the surface of the Earth, all what you need to know is the longitude and the latitude. You don't need a third point. So the Earth being rounded is also a two-dimensional space. The difference is that in this space, the sum of the angles of a triangle are 180. In a non-flat space, the sum can be anything you want, less or more, okay? So Einstein spent 10 years of his life to try to resolve this problem that has bothered Newton. How come things happen instantaneously? And the only way he could do it is by saying, okay guys, space is not flat, space is curved. So whereas special relativity took place on a bed, okay, that was completely flat, okay, general relativity takes place in a hammock, okay? Space صار بيلعب. In general relativity, there is no gravitational force. هذا كمان شيء مهم لكم انتم حتى تحكوا مع اصحابكم. Special relativity does not take gravitation into matter. It speaks about everything except gravitation, okay? A general relativity will take space will take gravitation, and mass will tell space how to curve. So if I have here a big mass, Earth is going to curve. Space will curve around the mass, okay? Space will curve around the mass. And this is what I wanted to show you here, okay? Space will curve around the mass. Objects will move around the shortest possible path. We all know this, that the shortest possible path in a flat space is a straight line. على الورقة بتروح from A to B. The shortest is from A to B is to draw a space line, okay? But if you take a plane, okay, you find out that they never go in a straight line because the shortest path will go around, okay, what we call a great circle. And Einstein came with the idea that light, okay, in curved space will take the shortest possible path. So mass will grip space by telling it how to curve, and space will grip mass by telling it how to move. هيدي حلوة كتير إنه mass will change the fabric of space-time, and the fabric of space-time will tell other masses and light how to move. So if you look at this here, okay, this is the light coming from the star. Here there's a very big mass. It is deflected, مثل بالبيار. Okay, we on Earth, because we are used to look at light going straight, we think it is here. Okay? So this light is deflected by the mass because it has to take the shortest path, and we think that it is here, and this is what we call, okay, gravitational lensing. مثل واحد عنده lens بالكاميرا تبعيته. If you look at this, this here is a quasar, which is like a star. Okay? Here you have a very heavy, very big galaxy, and the light is going to be deflected in a way that you will see several copies of the quasar, and you will not see the real one. And this is a picture taken by Hubble telescope. This here is the galaxy. The quasar that you're seeing here is only one quasar that is actually behind the galaxy. And we see 4 of it because of the deflection of light by space. And this specific one is called Einstein cross. That's why I put it here. Before we leave this, let's talk a little bit about black holes. Black holes were actually thought about, okay, in 1800, believe it or not, 1793, and by a priest. John Mitchell was a priest, and he said, okay, if light is made out of matter, if I throw it big enough, it could be out, go out, and never go back. And this is, now we know that if you have something that is extremely, extremely, extremely heavy, massive, okay, it will going to curve space so much that light cannot escape. And this is what we call a black hole. How do we know that black holes exist? By 2 reasons, by 2 facts. The first fact is that attraction here is amazingly big. So you see things going round and round, and you don't see anything in the middle, and you know they're going around a black hole. And the other thing is that when things are being actually, okay, sucked into the black hole, they will emit radiation. So we'll see radiation coming out for no good reason. So, just to recap, Einstein in 1905 wrote the special relativity. It took him 10 years to get to the general relativity. The difference between them is that in special relativity, gravity was not included, and the systems could not be accelerated, and the space-time was flat, whereas in general relativity, gravity is included, the systems are accelerated, and space-time is curved. And you remember when I told you, relativity, I tell you your time is shorter, my time is shorter, your distance is larger, my distance is shorter. This does not happen in general relativity because it takes into account acceleration and it takes into account gravity. So Einstein, within one lifetime, took 4 different things: space, time, energy, and matter. And within 15 years, okay, got them all into one theory where space, time, energy, and matter were all equivalent. And this is the genius of this man. And he was awarded the Nobel Prize. And he was awarded the Nobel Prize not for his relativity work that we spent the past half hour talking about, but he was awarded his Nobel Prize for his quantum mechanics. I'm going to spend the last 7 minutes that I have talking to you about quantum mechanics. And yes, yes. So, this was the third conflict. The third conflict was quantum mechanics. This is the Solvay conference in 1907. In 1907, Solvay was a big entrepreneur who every year used to invite all these physicists just for the fun. He was not a physicist. Pay them a trip to Brussels and tell them come and talk to each other. So this gentleman here, Planck, is the gentleman who started it all, okay? Near him, there is Madame Curie. For those of you who went to Collège Protestant, it is on Madame Curie Street. This gentleman here is Einstein, and we'll come to talk about the others. At that time, they had 2 problems. The first problem, if I ask any one of you which one of these blades is the hot blade, you will all know which one it is. يعني ما حدا رح يقول لي هيدي السخنة. فيك تمسك هاي ما فيك تمسك هاي, okay? This is what we call the black body radiation. It is a very fancy word of saying that, okay, any piece of metal, if you heat it, is going to emit radiation. Okay? If you heat it a little bit at 3000 Kelvin, it will emit in the red. If you heat it more and more, it will start emitting in all the range of the visible, and it will look white for you. That's why they will say it is white hot. Red hot شيء white hot أكتر. And nobody could actually find a way to explain, okay, how this curve worked. Okay, all the curve did not figure out. And then our friend Mr. Planck that we saw said, okay, this we can explain on one condition if we decide that light, okay, is not continuous. It's not a wave. It comes as particles. It's a corpuscle, okay? So let's just pretend for a moment, for mathematics' sake, that light is not a wave anymore, and that light is made out of corpuscles, and that's what he called the quanta. The other problem that was actually making people unhappy, and this is one of the papers of Einstein in 1905, is that in 1905, okay, they knew about the electrons, but they had no clue about the proton, the neutron, all this they did not know. And they knew that if you shone enough light on a circuit, you will have electrons that will skip from here to here. And they were trying to figure out how these electrons behaved, and this is what they called the photoelectric effect. Photo from light, electric from electricity. So I shine light and I get electricity. And they did not know how it worked, and it did not fit any of the findings did not fit the classical theory. I'm not going to spend time telling you about that, but suffice it to say that Einstein, as usual, Einstein was not a experimental physicist. He never went into a lab. He will take the experiment of other people, and think about it and sometimes take it at face value. And he said, the only way we can explain it is just to say that light is actually made out of corpuscles. Not like what Planck said, that I'm going to pretend they are. Light is made of corpuscles. And this corpuscles was called in 1926 the photon. So Einstein proves once and for all that light is actually, quantized. Light is actually a particle, but now it's a massless particle. Go figure. Yani what is a massless particle? We'll talk about it another day. So light is a massless particle. And even the physicist, William Bragg, he and his son got a joint Nobel Prize, and they did not understand this. So William Bragg says, physicists use the wave theory on Monday, Wednesday, and Friday, and the particle theory on Tuesday, Thursdays, and Saturdays. Because nobody understood what it was all about. Until quantum mechanics came, and Richard Feynman, who was actually, he's a Nobel Prize laureate for quantum mechanics. He got his Nobel Prize for quantum mechanics, and he said, I think I can safely say that nobody understands quantum mechanics. And then he said, nobody, including me. So we'll try to make it understandable, but this is also counterintuitive. So just as a recap, in 1900, Max Planck thinks that these energy is quantized. In 1905, Albert Einstein, proves that the photon is a massless particle. Thomson had discovered the electron, as I said, in 1897. And at the first part of the century, by 1932, we thought that actually this is what the universe was about. You had an atom with a nucleus. The nucleus was made out of neutrons and protons. Nowadays, this is what we think. We think that you have two kinds of particles. Particles that are used to make matter, and particles that are force carriers. You remember when I told you that Einstein said that gravity is not a force, gravity is geometry. In quantum mechanics, forces are particles. I told you it's counterintuitive, so you have just to accept it. So we have two kinds of particles, the particles that carry the force, and we have four forces, and the particle that will actually make matter. We have four forces: gravity, strong, weak, electromagnetic. Now we have theories that have actually merged the electroweak theory, and we hope to be able one day to get to a theory of everything where we can have gravity, strong, weak, and electromagnetic forces as part of one force. And just for fun, Georges Lemaire, who was actually a priest, made calculation, and he said, okay, then if this is true, the world must have started from one original single point. In 1927, he made these calculations, and a gentleman called Hoyle, عم بتمسخره, قال له, يعني you mean to say that the world started in a big bang, and the world stuck. And this is where the word Big Bang Theory comes from, because Georges Lemaire said this, and Hoyle, said that words are like harpoons. Once you throw them, it's very difficult to retrieve them. So now we are stuck with four forces. I still have 4 minutes, so let me just go very quickly. The double split experiment, for those of you who have heard about it, for the others, just give me 2 more minutes. If I am shooting billiards through holes, this is the kind of pattern I get, If I shoot only through one hole, they're all going to be mostly on that side. If I shoot only through the other hole, they're all mostly will be on that side. If I shoot through the 2 holes, this is the pattern I get. And this pattern is a pattern of matter. This is a pattern of corpuscles. If I have light going in, as we said, we have the interference pattern, You remember when we spoke about the water interfering? You get an interference pattern of dark and bright lines. The bright lines are where you have the crest, and the dark lines is where you have the trough. So you remember Mr. Thomson, who discovered the electron in 1897? Okay, Thomson discovered the electron in 1897, and he says there's a new particle in town called electron. His son does the double-slit experiment with electrons, and he has an interference pattern, and he said, no, Dad, this is not a particle, this is a wave. And this is one of the tenets of quantum mechanics, which is the duality between particles and waves. We don't talk anymore about particles or about waves. We talk about things behaving as particles and behaving as waves, depending on the way you look at them. And this here is a cartoon from the New Yorker in 1941, where this gentleman going here, he becomes a wave, he goes around the tree, and he becomes a particle again. So what is even worse, عندي بعد دقيقتين? What is even worse is that if you observe from which slit these are going, you lose it. So the waves or the particle know that you're observing it. And this is why, okay, you have this, this is what happens. I'm just going to go here but to tell you that this is also important. The same old Feynman, a philosopher, once said, it is necessary for the very existence of science that the same conditions always produce the same results. Well, they don't. And this is something that we learned from quantum mechanics, okay? And if you think that this is something that is very far from you, I want to just show you the last slide. Okay. Next time you take your phone, the phone is made possible because of quantum mechanics. The transistor could not have seen the light without the quantum mechanics theory. And when you take a picture and it is tagged on your GPS, you took this picture in Bathish Hall, this relies on GPS, which actually relies on general relativity. So every time you use your phone, you're using the progress that you made in general relativity and in quantum mechanics. And now we're hoping that one day somebody as genius as Einstein will be able to actually merge them together. Thank you very much for your time.